So we're starting our new unit of electrostatics, which is really part of the study of electricity. And our understanding of electricity is fairly old because people have been noticing the phenomena related to electricity for a very, very long time. One of the very common experiments that's been done forever has been done with balloons and fur. You know, since ancient Egypt, they've had balloons. And if you rub a balloon against hair or fur, you guys already know that after you do that, it will there will be an attraction between them. Now, what's important to notice is that before you do that, there's really not. If you put a balloon next to somebody's hair but you haven't rubbed it first, nothing really happens. It's only after the rubbing takes place that suddenly this new behavior is observed. And it doesn't have to be a balloon and fur. You could do it with like silk and rubber, or you could do it with I don't know, some kind of wool and glass. Like any two materials, even like one type of fur and another type of fur will demonstrate this. So I'm going to be talking about a balloon and fur just because that's kind of familiar to us. I didn't say hair because that's just, I don't know, it felt weird, felt creepy. So we're going to talk about balloon and fur. And you guys already know that if you had the balloon and the fur, so that's the balloon is this rectangle and the fur is that circle. If you had those two things, you guys already know that they would be attracted towards each other. But what you maybe haven't tested, but you're welcome to if you'd like, is if you got two balloons and you charged both of them up by rubbing them onto somebody's, now I'm going to say fur, and that sounds even worse. Anyways, you rub a balloon. Now, just the word rubbing is bothering me. Anyways, so you rub a balloon against, like, rub it on somebody's hair, rub another balloon on somebody's hair. If you hung them from strings and you tried to bring them near each other, they would actually repel each other. Uh, and so again, this is something that people have noticed for a very long time. And the same thing will happen with the hair or the fur or whatever. If you got pulled two of those hairs out that had been rubbed and you tried to put them towards each other, they would repel and they'd push apart. So these are interesting phenomena. And as they're going along here, the initial idea was, well, everything has an opposite, and the opposites will cause them to attract, and the like things will repel from each other. But there's another wrinkle in this particular model of understanding charges, which is what charged objects do with uncharged objects. So both the balloon and the paper were both charged. Gotten rid of the vowels. That was saved so much time. But if we had like an uncharged like little piece of paper, so uncharged piece of paper, if you brought the balloon near that, there would be an attraction there. The balloon and the piece of paper would attract to each other, and it does go both ways. If I had the piece of paper, I don't know, somehow like in a fixed position, and I brought the balloon nearby, the balloon would attract towards the paper. Or if I was holding the balloon and I brought it towards the paper would like jump towards the balloon. So there's an attraction there. If I brought the fur near those pieces of paper, they would attract towards each other. But then if I brought like the paper near itself, like just put two pieces of paper next to each other, we get nada. Nothing happens. And that started to make people wonder because they're like, okay, we were okay where it was like opposes like and opposites attract. But now we have this thing where it's attracting to both kinds, but it doesn't do anything on its own. So definitely we don't have the like repels like thing because the piece of paper don't care about each other. And so what eventually came out of it is the two charge theory. And the two charge theory works like this. There are two types of charge, that goes without saying. There is a positive charge and a negative charge. And everything has either a positive charge or a negative charge or a combination of both of those charges so that their total is zero. And if you have two positive things, they will repel. And if you have two negative things, they will repel. But if you have positive slash negative things, if you have charged things, they will attract towards those neutral things. So we have two charges, and we know always they will repel if they have the same charge, or they will attract if they have different charges. So we've got to write that down because even though I'm sure most of you guys know that, we attract when we have opposites, and we have to repel when we have the same. And then we have the uncharged attracts to charges. So these are the pieces of the two-charge model. And it works really well. Even though they had no idea what the scientific basis really was behind this, they had plenty of empirical evidence that when they tried other objects, they could decide whether it was positive or negative based on how it behaves towards known objects. So if I draw in a new object here, if I draw in a pentagon for whatever reason, and I call it rubber, oh wait, rubber's kind of the same as balloon. Let's not do that. Let's do glass. Sure, glass works fine. If I had a piece of glass and I rubbed that against fur or silk or whatever, um, I could then test it, and if it attracts towards the balloon, then we would know that it has an opposite charge or it's uncharged. If it repels from the fur, we would know that it has to have the opposite charge of the fur. That's the two-charge model. You need to be comfortable with these ideas, and you may see questions that give you like object X repels this, object Y attracts this. Tell me about what the charge of Z could be, and the options are going to be it's either positive, negative, or uncharged based off the behaviors that you see. Okay, so now that we've talked about that, this is stuff that they've known for a long time, and it turns out they kind of did a bad job because when they decided what was going to be positive and negative, they had no idea what was really responsible for all that, which was electrons. And so electrons actually carry charge, and they have a charge of 1.6 times 10 to the negative 19. The units are called coulombs. Coulombs. So that's a very, very small number. When we think about something like 1 coulomb, which is kind of like the number that you might come across with like a charged up balloon, uh, that's made of many, 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 many electrons that have been added to that. But the problem there is that electrons are actually negative particles, and scientists for a long time wanted to talk about positive charges because it was just more convenient to think of things as positive charges, even though the real charge carriers tend to be electrons. So uh, this is the charge magnitude, this 1.6 times 10 to the negative 19. Any object has to have a charge that is some multiple of that because it's going to have some number of negative electrons. Oops, why isn't that working? Some number of negative electrons, so we'll call that n, negative electrons, and it might have some number of positive protons in the nuclei, and that total of m minus n is going to give us its charge, whatever the positive minus the negative. But the number of protons can't change because you can't rub off something's protons. You can transfer its electrons pretty easily. So really, it's the electrons that move stuff around. But because we always have one electron or two electrons, we can't have half an electron. You could never find something that had a charge of like 1.2 times 10 to the negative 19th. That would be impossible because that would require a fraction of an electron, and that can never happen. So it's okay if we have 3.2 times 10 to the negative 19. It's okay if we have 4.8 times 10 to the negative 19th, but we can't have something like 3.7. That would be impossible. So these are the basic ideas behind charge theory. I want to just say one more time, electrons are negatively charged. And they are the charge carriers that are going to explain all of the behaviors that we see here. But it doesn't actually matter. All of the theories, or many of the theories that were made about electricity, were made before we knew about electrons. And none of those theories, or none of the ones that we still have, were thrown out when it came out that we had negative charge carriers instead of positive ones. So all of the theories still work with positive charges. And if you hear me talking about positive charges moving around instead of negative charges, while from a chemistry type perspective, I'm technically wrong. Almost every single like electrical based text just talks about positive charges and just doesn't care that they're actually negative charges because it doesn't really make a difference. So if you notice that there's that um, that I'm not in sync with like electrons and talking about positive charges, that's all there is. If it makes you feel better, if I say positive charges, what I'm really talking about is holes that electrons should be in, but because they're not there, now it's positive. And that clearly makes it way better. So there's the video on charge theory. Sorry it went a little bit long, but there's a lot to unpack there.